Let's look at the radiation boundary conditions now. Now, before I get into that, one general principle we will derive. So, supposing I have a unbound medium. Now, we know that the solution to Maxwell's equation, so this unbound medium follows the Helmholtz equation, right, and we know that the solution to this is a plane wave, right. So, what is the solution of, what is the kind of solution that I get? E is E naught okay. I am ignoring the time dependence, we have already taken care of that. So, this is the plane wave solution over here, and you can see that if I plug this into this, I mean this is coming from the solution to this Helmholtz equation, right, it satisfies it identically, right. Everyone is convinced? The first term when I take del square, I am going to get a kx square plus ky square plus kz squared, which is equal to the second term over here. There is a minus jkx. When I take one more derivative, it will become minus kx square, minus ky square, minus kz square, and there is a k squared over here, right. So, it will cancel off, I will get 0. So, you agree that this is a solution. Now, let me ask you the following question. Is this also a solution? So, I call E is equal to, I make this E naught now a function of k. So, what have I done? I have made the amplitude to be dependent on the wave vector. Does this work? So, some change I will have to make over here, but let us see, if I substitute this in here, what happens? What is the first term going to do? Del squared. Will it give me, see, the del squared is only going to act on the spatial terms. The spatial terms is only e to the minus jkr. So, what will I get from here? I will get a minus kx square minus ky square minus kz squared, correct. What about the second term? K squared. So, does it cancel off then? Yeah, so the first term is going to give me a minus kx square minus ky square minus kz square. I am writing this k as kx, ky, kz, right, the vector. Right. So, the first term is giving me a minus kx square minus ky square minus kz square, and what happens to the second term? Yeah, so the slight problem over here is that I am using k as both a variable of integration and the constant k in the equation. So, maybe that is a bad idea. So, what should I, let's not use k, let's call this by some other thing, okay, let's call this, let's say p, and let's call this p, okay. Now, can I say that this satisfies, right, plus k squared, right. So, this integral over different values of p does not actually do anything. So, if this is a solution, this is also a solution, right. So, what is this, what is an interpretation of this general equation that I have? Superposition of different plane waves, that is what it is, right. Amplitude is varying and it is like a Fourier transform idea, like a superposition of different plane waves, right. So, the general idea behind this is that any wave that is travelling in free space, I can write as a collection of plane waves, Okay, so yeah, spatial frequencies. Not omega t. That is the same. Yeah.
Some function in space.
Yeah.
Is some function in space and you are
Separating them out. So this is not exactly needed to derive this boundary condition, but it's a good intuition to have. Okay, so we'll just keep this in the background. Okay, so now let's look at let's go back to our a wave that is traveling in a general direction k hat. Okay, so in let's say a homogeneous medium, we know that a plane wave is traveling, right? So when I do something like curl of h, so what is curl of h is equal to minus j omega mu, sorry, yeah. So this is minus, so this is j omega epsilon, entire epsilon e vector, right? This is what I have. Okay. Now h, you know, is of what form? H naught e to the minus j k dot r. We know this. What kind of terms does curl of h have? So curl over here will have what kind of terms? D by dx, d by dy and d by dz. Okay. So when I do this expression over here, when I try to evaluate curl of h, and h is of this form, so whenever it encounters a del by del x, what will happen? Minus jkx will come out from here, wherever there is the x part. Similarly, there will be a minus jky and a minus jkz whenever these derivatives are encountered. Okay. So you can do this simplification, that the act of putting del cross is for a plane wave equivalent to this. Okay. Okay. Many of you may have seen this simplification in your undergrad EM course, that for a plane wave I can replace this del cross by just a minus jk vector. Okay. I just gave you the intuition for it, but you can derive it rigorously. Okay. This further I can write as minus jk k hat cross h. Okay. So you can straight away see what we are going to do. This is the expression that a plane wave satisfies, right? So an expression satisfied by a plane wave. Right. So what is the left hand side? Curl of h. There is a derivative involved. What is the right hand side? Is it linear in h? It is linear in h. There are no spatial derivatives or anything, right? There are some other constants over there. So this is the same idea here in 1D which I had. The expression obeyed by a plane wave, du by dx was proportional to u. Exactly the same situation is going to happen over here. Curl of h is proportional to h. Of course, there are more vectors and all over here, but this is the basic idea that we will use to derive the boundary condition. Okay. So let's draw a vector, right. So this is my k vector. So as long as, so the wave is traveling over here, my E and H are going to be in orthogonal directions for a plane wave, right. So at any point if you ask me, this expression is obeyed. Okay. Now what is, let's go back and see what is the kind of term that we have to worry about, right. So the kind of term we have to worry about is here, this dotted part over here. Okay. Tm is anyway going to be my choice. What am I left with is this expression, right. Now this expression can also be rewritten in the following way. So, I have A cross B dot C, right. Can I, if I swap the order of the cross and the dot, what happens? Negative sign. So, this expression can also be written as, can I write it like this, dot. So, dot right, 2 minus signs and I get the same expression. So, it would have first become minus Tm dot 1 by epsilon r curl of H cross n, and A cross B is minus B cross A. So, the n comes to the middle. Okay. Alright. So, the expression that I really have to worry about is this guy over here. So, what is this? Let us rewrite this expression over here. So, I have n cross 1 by epsilon r curl of H. This is the term that I want to get an approximation to. Agreed? The rest I can take care of. So, what can I do over here? So, what I say now is, this is the so called leap of faith. If I assume that my boundary over here is this, such that the plane wave is hitting this at a normal incidence, then which direction is n hat? This dotted line is my boundary, okay. So, this my wave is inside this region over here. So, which way is my n hat? So, okay, what I am saying is that I have this dotted line which is the computational domain, okay. This is the computational domain. I have a plane wave that is travelling in this direction, okay, hitting the boundary normally. Which direction is n hat, right? So, n hat is also along in this special case, okay, only in the special case. So, in that case I can replace this for this special case only, for this special case. What can I write this as? I can write this as n cross 1 by epsilon r and replace the rest from this guy. So, minus j k n cross h. So, this is true for a plane wave hitting gamma. So, this was my gamma normally. Why? Because I simply replaced my unit vector k hat by the unit normal vector n hat. So, no one can object to this, right? No, so this epsilon r is for a homogeneous medium. I mean, epsilon r is not a function of space over here. Why? Because if epsilon r is not a function of space, then I can safely assume that the solution is a plane wave, correct? We know that for a homogeneous medium, Maxwell's equation gives a plane wave solution of this form e to the minus j k dot r.
So this epsilon is at the boundary.
This epsilon is in the neighborhood of the boundary. It may be vacuum or it may be some homogeneous medium like water or something. Let us say you have a radar wave travelling underwater and the antenna underwater, then it is the homogeneous epsilon of water, right, whatever it is. But what I am talking about is, first of all, I need to have a plane wave, and next of all, the plane wave should be hitting the boundary normally. So, if you notice that I mean, when we do FEM calculations, we will have the scattering object and surround it by some amount of vacuum and then terminate the computational domain. There is some amount of air. No. What we do is, so let us say this is my aircraft over here, okay. Now, question is, in this, where should I draw my computational domain? Should I just make it tightly fitting with the aircraft or should I expand it a bit, right? So, the computationally inefficient but easier thing to do is to make my domain like this. So when I do this, I have to discretize all of this free space region, okay, and that's a price I pay, and we'll come later on what is the advantage and disadvantage of doing. But when I do this, now when I look anywhere close to the boundary, because it's free space, Maxwell's equation should be satisfied at each point in space. Free space or homogeneous space, I will get a plane wave. So plane wave solution is valid. Further, if this plane wave were hitting the boundary normally, then this expression holds, right? So this is what is called your, either you call it the radiation boundary condition or first order. No, by boundary I mean the outermost boundary. Outermost boundary. Absorbing boundary condition. Okay. Why are we keeping 1 by epsilon r there? Yeah, so why? So question is, why are we keeping this 1 by epsilon r? Huh? Well, because if epsilon r were a function of space, then technically speaking, I may not get a plane wave like solution over there. So the approximation of replacing curl of h by k cross h will not be valid. Okay. Right. So what I am here, so the big leap of faith is going to be that everywhere in my right hand side, okay, this expression over here, so in the weak form RHS is going to be replaced by, so what did I have earlier? I had Tm dot n hat 1 by epsilon r curl of h, what else, dl. This is what I had earlier, and this is the exact form. Now what am I replacing it by? I am replacing this by Tm dot this whole expression. So n cross h minus jk by epsilon r dl. So is this always correct? Answer is no. When is it not correct? So the first thing is not correct when the direction of propagation of the wave is not equal to n hat. For example, if you look at this aircraft over here, let's say the incident wave is coming from the left hand side like this, it's possible that it hits this aircraft over here and the wave goes off in this direction, right? So now n hat is here and the wave is hitting non-normally. But what approximation am I doing? I am assuming as though everything is hitting normally. So, but I am still using this expression. So this is the price that I am paying for the convenience of a very simple boundary condition. This expression that I have written on the right over here is very simple to implement. The problem is it's exact only at normal incidence. So if I now make the computational domain larger and larger, right? So this becomes more and more accurate because waves will more or less begin to reach it normally. Think of a very large circle, right? Whatever reaches there will reach only normally, assuming a finite object, okay? So whatever hits non-normally, what will happen to it? Because this boundary condition is not exact, there will be a mathematical reflection, right? So what will happen is this hits it like this, and due to the approximation, some wave will get reflected back. This is inevitable if I use this. So this is what is, so that's why I have called it a first order absorbing boundary condition, okay. It's called absorbing boundary condition because it appears as though it is absorbing everything that is going out. Nothing is reflecting back, that's why it's called absorbing boundary condition, right. So not correct when this n hat is not equal to k. What else is not correct about it? Well, this is the main thing. So leads to numerical reflection. Therefore, larger computational okay. So people have built, so let's say if you wanted to improve this, okay, we won't do it here, but what would you try to do if you wanted to improve this? Change the shape such that it's always getting reflections at normal incidence. That becomes tricky to do. If I am particularly writing a general purpose solver, I don't know a priori what is the shape of the object that's going to go in. So, for example, here what are we doing? We are imposing that the reflection go to 0 at one angle. A second order boundary condition will allow you to make the reflection go to 0 at 2 angles. Third order will allow you to do it at 3 angles, and so on. The mathematical form will become more and more complicated. Okay. And when you look at the mathematical form of higher order boundary conditions, you will realize, let's stick to first order boundary conditions and pay the price by making my domain a little bit larger. Okay. So, this is very, very commonly used boundary condition. Okay. So, your first code that you write, just implement this, get it working. On top of that, then you would try to implement higher order boundary condition. No, so the word absorbing is slightly misleading. What is happening is we are simulating the condition for a wave to go off unreflected. That was our original motivation, because this expression was the expression obeyed by a plane wave that is going unhindered. And when I draw a mathematical boundary there, nothing will come back, because that's the equation that physics has given me. So, it's as though, supposing I had a perfect absorber there, something that absorbs and does not reflect, that would do the same thing. So, that is why some people called it absorbing boundary condition. Nothing came back. So, it is like, right, if I was sitting inside the domain, supposing I was standing here, for this observer what happened? A wave went off, never came back. What is the one way of thinking about it? It was absorbed. Right. So, hence the word absorbing boundary condition.